I'm telling you, one key principle which we discovered is algorithm need not be complex. It can be simple but very effective. In fact, Bayesian will fall into that category. So let us recollect our funda. This is very important because without that you cannot go forward. So we all know what the probability is, right? Probability of an event happening is number of favorable events by total number of events, right? So let's take example of a coin toss. Probability of head is 0.5 because number of instances is 1 where head can occur and total number of instances is 2. Similarly, probability of hitting 1 in a dice is 1 out of 6 because there is a total number of possible outcomes is 6 and you have only one favorable, which is 1. So that is basically talking about generic probability. So when you talk about probability, think of it as a ratio. Ratio of the number of favorable conditions out of total number of events, or number of favorable events by total number of events. So what we use typically in a generic probability is assume that you have looked at all the history of such events happening. And then in this history we found that suppose 1,000 times you have looked at you know a day, a normal day, and out of that you say that typically, you know, out of the 365 days, or sorry, out of 365 days, you've seen that historically around 10 days it's been raining, or let's assume 20 days. So the probability that it will rain typically will be 20 out of 365. But let us go with a little bit more focus. Suppose out of 365 days, there are cloudy days are suppose something like 10 days. So probability of a day being cloudy becomes 10 out of 365. Now assume that all the, so we talked about 20 days as having rained, right? 20 out of 365 probability for rain, and probability of cloud being 10 out of 365. But we also know that probability of a cloudy day, sorry, a cloudy day, it was when it was raining, is all the days, all the cloudy days it rained. So their probability that it will rain on a cloudy day is 100%. So you see the difference between generic probability, which is when we don't have any extra condition, we say that we just want to know probability of a rain, which is basically frequency of rain versus total number of days. So that becomes 20 out of 365 if probability of rain is 20 out of 365. Same way, independently, number of days cloudy, let's assume it is 10, this probability of it being cloudy is 10 out of 365. So, but we also know that of all the 10 days which it had been cloudy, it was raining. So here is where we have this notion of conditional probability. So if you have a condition A, let's assume condition A is cloudy, probability that it will rain, which is say let's condition B1 here, probability of it raining given that it is cloudy, which is A, is same as assuming the number of days for both being cloudy and rainy. By total number of days, it is cloudy. In our case, it was 10 out of 10, right? So it becomes 100%. But let's take the other way. What is the probability of A given B1 here? What is the probability that it has been cloudy given that it is rain? It becomes P of A intersection B1 given P of B1, right? What is P of B1? It's not 20 out of 365 and intersection is 10. So there it becomes 50%. So you see there's a difference if you change the order in a conditional probability. Probability of it raining is 20 out of 365. Probability of it being cloudy is 10 out of 365. But probability of both is 10 out of 365. Now we're talking about conditional probability of it raining having been given a condition that it is cloudy, which is P of A, then it becomes 100%. But if you take the other way, probability of it being cloudy and if it is raining is 50%. Is that clear? This is a very important element. There is a difference between what is known as absolute probability and conditional probability. Absolute probability for cloudy it was 10 out of 365, and cloud in case of rain it was 20 out of 365, right? But what we also want to tell is if you were to look at probability of intersection of both, it is same as condition of probability of one multiplied by conditional probability of the other given this. So probability of A intersection B is same as A intersection B is equal to probability of B into probability of A given B. Very important. It is again ulta also is the same, which is if you take probability of A and B intersection A, that also is same as probability of A intersection B. So in our case, probability of A intersection B is, let's take probability of rain, it is 20 out of 365, and what is the probability of A intersection B, which is having rained? What is the probability of being cloudy? We saw it is 50%, right? So 50% of 20 out of 365 is 10 out of 365. That's what we got as the number of days where both were there. It's cloudy and rainy. You take it the other way also, 100% of 10, it becomes same, 10%, 10 out of 365. You either do 50% of 20 out of 365 or 100% of this. So why is this important? This is important because in several real scenarios, you actually have to look at probability of a following event after having observed an initial event. You don't work typically with absolute frequencies. We'll come to examples. But the important theorem here is that you need to look at all the possible choices which are present when you're talking about a specific event. Let's assume that a event B is made of two events, B1 and B2. So you talk about conditional probability with respect to A of B1. Actually, you should be understanding that typically if you take a probability of an event A and you have multiple dependent events on which it is dependent, so independent events on which it is dependent, you see that P of A is P of B1 times P of A given B1 means A if B1 has occurred, P if B2 has occurred, or so on till Bn. So because B1, B2, Bn are the possibilities, and you will look at the corresponding probabilities and multiply them, and you'll generate the probability of the consequent event. So the Bayes theorem is basically a very simple idea of you have observed a following event, an effect, which is A, and then there are several causes. It is up to K, B1, B2, B3. So what the Bayes theorem says is that probability of one of the causes having caused this effect, which is BK, having observed an effect A, is the corresponding conditional probability of A if BK was occurring times probability of BK absolute probability over summed up sums of same combinations. Make it clear. Basically, we're talking about two things here. There are several possible causes of an effect. We're trying to see if we have observed the effect, what is the probability that it is caused because of this particular cause? Out of suppose you have two different causes, what is the probability that it is caused because of the first cause? Let's take example of wet garden. It could be it has rained, it has not rained. Right? Simple two conditions. If we take prior probability, which is normally when it rains, it says 40% of the times it rains, PB1. PB2, which is not raining, which is 1 minus 0.4, which is 0.6. Now assume that 90% of the time, if it rains, it is wet floor. That is P wet floor given that, wet garden given that it has rained is 0.9. But it is also possible that there is a wet floor if it is not rain, that is around 20%. So now what we need to understand is what is the probability given that you have a wet garden, what is the probability that it has rained. Again, going by same principle, we look at what is the condition of having rained given that you have observed a wet garden. How do you infer? You infer it in this format. You look at what is the probability of rain, what is the probability of not rain, multiply it with the corresponding conditional probability of wet garden given that condition, and then do the appropriate fraction. So you see here 0.9 is the condition probability of wet garden if it had rained. 0.2 was the wet garden condition if it had not rained. So what we'll do is we'll multiply 0.9 with a priori probability of rain, which is 0.4, and then we'll multiply 0.2, which is conditional probability of rain, sorry, not rain, having observed wet garden with no rain. So what does it give you? It gives you something like 0.75. It means that 75% likelihood that the wet garden is caused by rain. Same way we can take 0.12 by same thing, that becomes a conditional probability of it not having rained given that you have observed a wet garden. What is 0.12 divided by 0.48? That becomes 25%. But what does it mean? It means that it could have been because of something like, it could have been something because of some sprinkler, some lawn water source. So what Bayesian theorem allows you to give you is it allows you to identify potential what you call causes having observed certain effects. Abstract it out at a higher level, you are observing some symptoms. Now you're trying to identify root cause. There could be several causes. So Bayesian approach is one approach to diagnosing. This is actually called as diagnosis. So diagnosing the root cause of what you have observed. So that is why it is very important for us to keep in mind. No, it doesn't work with, actually it is works with several variables. In fact, generic one, it just says A1 and A2 and A3. You can do it with any number of variables. But Bayesian condition is very simple. It says having observed, it works with many variables. We have more complex equations there. Only thing is, it is a generalization of this. So why is it useful in machine learning? In machine learning, your one of the special use case we talked about was diagnosis, right? Recommendation systems or diagnosis, where you see what is the symptom and you try to identify what are the different causes.